Introduction to mathematical induction. So in mathematical induction problems, we will have a proposition that reads something like this, that says, for example here, the sum from 1 to n of k squared is equal to 1 over 6 times 2n to the power 3 plus 3n squared plus n. And we want to prove that this proposition is true for all, this symbol reverse a means for all n larger than or equal to 1. And now we want to use the principle of mathematical induction to prove this. So first, what is the principle of mathematical induction? It's sort of a logical way of thinking to be able to prove things for infinite amounts. So if you imagine a ladder here, just a ladder, I don't draw great, but bear with me, and these are a bunch of steps, then mathematical induction is a logical way to prove that there are infinitely many steps up here if we keep looking, but without actually looking. And the way we do that is, first step is we show that the first step exists, and then the second thing we do is we assume that some step somewhere exists. We just say, just given a certain step, okay? So it's just an assumption, it's not a full statement, it's just saying let's assume that this step exists. But it's not actually this specific one, but just to make it easy to visualize for you, I colored it, but we generally just say that assume that some step somewhere exists. Then, if that assumption is true, then follows the proof of induction, which says that then the proof is to say that if this one exists, then I can prove for you for sure that this step here, the next one, actually exists. So by doing this, basically what we're saying is, okay, if there is some step, then I can always prove, this number 3 guy can always come in and say, well, if there is a step, then I can prove that the next one exists. And then this number 1 guy we do, then it's enough for us to just show that the first step exists. Because once we've shown this first step exists, then the assumption is valid for this step, and then this number 3 guy can come in and say, oh, there is a step? Okay, that means the assumption is true, so I'm proving to you that the next step definitely exists. And then the third guy again looks and says, oh, number 2, this second step also exists. Well, then the assumption is valid for number 2. So then I can show you for sure that number 3 exists. And so on and so forth. And by that logic, you've proven that all the steps exist, because this number 3 guy will always step in to show that the next one exists. So that's the principle of how it works. You assume that some step exists, and then you introduce a proof that shows that if that step exists, then the next one definitely exists. And then it's enough to just show that the first step exists, so that the second and third and so on and so forth will also follow. So how do we do that in a mathematical question like this? Well, first thing we do is we prove that the first step exists. So basically what it is we just prove that the proposition here, I call it P, is true for n1, n equals 1. So that's what our first step basically is. And what we do there is we just look at this expression and we just write number 1 wherever we're supposed to write an n. So if we look at the left-hand side on its own, left-hand side, it's going to be k squared, which is going to equal 1 squared, which is 1. And then if we look at the right-hand side, which is this part here, then it's going to equal 1 over 6 times 2, 1, plus 3 times 1, plus 1, which is equal to 6 over 6, which is equal to 1. So we have that the left-hand side equals the right-hand side for n equals 1. And so the proposition is true for n equals 1. So now we've just shown that the first step exists. That is nowhere near showing that all the steps exist. But we have the first one. Then we can go on to the second part, and we can do the induction assumption. The assumption, we call it, the induction assumption. So we're just going to assume that some step somewhere exists, which basically means that we're just going to assume that P is true for n equals some number P, small p. Just some number, doesn't matter. And basically we just write out exactly what we have here. We just write P wherever there is an n. That's all we do. Because this step doesn't really show anything. It's more just like saying, okay, if we assume that somewhere this exists, then it's going to look like something like this. And it's exactly that. I just wrote P where there is that. And now we come to the actual calculation. And then here we look that if number 2 holds, then n equals p plus 1. So we look at the next step, when n is a step ahead of the assumption, just like we did here. When n is equal to p plus 1, so the next step, then this is what we get. Then n equals p plus 1 will give us what? Well, we're just going to calculate this with the left-hand side and the right-hand side. So if we look at the left-hand side first, we're just going to write a p plus 1 wherever there is a p. So we write p plus 1, 1 k squared. And here it's kind of tricky because here's where we want to use this expression of the assumption. So we want to write this in a way that we can actually use this. And if you look at this, what does this really mean? Well, it's a sum of numbers k squared from number 1 to p plus 1. So it's like k squared when k equals 1, plus k squared when k equals 2, plus when 3, when 4, when 5, up until when it's p, and then when it's p plus 1. So it can be rewritten as saying it's the sum up until p plus the term when it is p plus 1, which is p plus 1 squared. Just put the p plus 1 instead of the k. So it's the sum up until number p, and then there's only one number left. We just add it, which is p plus 1. This is just that. So now we can see that this is exactly what we have in the assumption here. This expression is exactly what we have in the assumption here. It's the same one. So it equals this here. So we're just going to put this in here, plug it in, and then calculate what this gives us. So basically we just write 1 over 6, 2p3 plus 3p2 plus p plus 1 squared. And that's what that equals. It's great. So pause the video right now. I encourage you to do this calculation here because I don't have all the time in the video to do it very detailed. I'm just going to write what it's going to give us. So pause the video and try to do it. And now I'm going to give you the answer to it. And it's just 1 over 6, 2p3 plus 9p squared plus 13p plus 6. And that's our left-hand side. Great. Now what we want to do, obviously, is we want to calculate our right-hand side and see if it equals it. So our right-hand side is basically just what we have here, but instead of p, we write p plus 1. So it's just going to be 1 over 6 times 2p plus 1 to the third, plus 3p plus 1 to the second, plus p plus 1, not squared, just p plus 1, because we just had a p there. That's it. And then again, I encourage you to calculate this on your own, and I'm just going to give the answer here. So you can pause the video now. And the answer is, well, it's going to be 1 over 6 2p3 plus 9p squared plus 13p plus 6. And you notice here that it's great because our answer here is the same as our answer here, which means that our left-hand side equals our right-hand side. So we have everything is true. So we've shown that if some step somewhere exists, then the next one will exist. It's valid. And then we've shown that the first one exists, which means that the second one exists, and the third one exists, and the fourth one exists, and so on and so forth. So we have proven that this expression here will equal this as for all n larger than or equal to 1. But in the end of the question, when you've done this, this is the main calculation part. But in an exam, or if you're answering the question formally, it's always good to write a statement, something like this. I've written it out, that just concludes the logic to show that you've understood the logic. And it basically is just something like, we have shown that the proposition is true for n equals p plus 1 if, in case, it is true for n equals p. And since it is true for n equals 1, then it must also be true for all n that are larger than or equal to 1. By the principle of mathematical induction. Make sure you write this out because it's important to mention that you've used this principle if you are proving this in an exam. All right, I hope you've understood what the principle of mathematical induction is, and hope to see you in the next videos. Thank you.